Hello everyone, we are here to present a project IoT-enabled AI system for real-time AQI monitoring and asthma protection. This project was conducted by Vivek Nair, Soumya Desai and Suyash Kondiskar under the guidance of Dr. Kriti Srivastava. In the next few minutes, we'll just quickly cover the problem, a solution, and then dive into what really matters, that is, how we tested it to make sure it works. Moving on to the objective of a problem. Why did we choose this? Asthma affects millions, and air pollution is a major trigger. This image shows how various pollutants worsen asthma, leading to increased symptoms, hospitalizations, and decreased lung function. Current air quality systems often don't provide the personalized, timely warnings that asthma patients desperately need. That's the gap we are addressing, creating an AI powered system tailored to them. Think about someone you know with asthma. Imagine how helpful it would be for them to get a precise alert before going outside on a pollution day. So, what's the core problem? It boils down to these four key issues. First, pollution triggers asthma attacks. Second, current systems aren't personalized or real time. Third, asthma patients don't get timely alerts. Fourth, we need an affordable personalized alert system. Has anyone here checked the air quality index today? Is it specific to your street? Probably not. That's the problem. Our solution uses AI to predict air quality. We gather data from sensors, historical records, and APIs, feed it into our AI, and generate personalized alerts and visualizations. Think of it as a weather forecast, but for air pollution and tailored to an individual asthma threshold. We have used these two sensors, PMS 5003 and Groove multi-channel gas sensor, to get the real-time data, transmit it with this module ESP32, and store it in the cloud Supabase. This is the foundation of a system, accurate real-time data. Our AI model uses a powerful algorithm called XGBoost to predict the pollution levels. We clean the data and used past pollution levels to make accurate forecasts. In simple terms, it learns from history to predict the future. And to provide personalized recommendations, we use an agentic RAG system that combines the live air quality with a patient-specific information to give tailored advice needed for the patient. This is what makes our system truly patient-centric. This diagram shows the whole flow of a system from collection of data to the AI processing and providing alerts out to the user. It is a complex system, but the key is it's designed to be seamless for the user. This is the hardware architecture and the components, the microcontroller and the sensors. They are the eyes and brains of a system in the real world. Now let's get to the crucial part, testing. We didn't just build this, we rigorously tested it in three phases to ensure it's reliable and accurate. Testing is what proves that a system works in the real world. So, the phase 1 was all about sensor calibration and basic testing, where we made sure that our sensors were accurate. We verified the readings on a monitor, tested it in a controlled room, introduced pollutants like a matchstick to see if they reacted correctly. Imagine a faulty thermometer. Useless, right? We had to make sure that our sensors were spot on before moving forward. Phase 2 was focused on getting the data to the cloud reliably. We wrote a script to send the data to Supabase, check that the cloud data matched the local readings, and optimize how often the data was sent. Think of this as setting up a strong, consistent communication channel, no dropped calls, no lost data. And phase 3, the last but not the least, field testing and diverse environments. Phase 3 was the ultimate test because it was deployed in a real world environment. We choose a diverse location based on the near and the far from the official stations with different pollution sources with varying AQIs. So initially we selected 5 of these locations for our field testing. First is Bayanda Mira Road Belt, second Cooper Hospital, third RA Forest, fourth Vasai East and West, and fifth a Mumbai Metro Transit from Cooper Hospital to the RA Forest. So this is the AQI graph of the journey from Bayanda station to Mira Road, where earlier we were standing on the Bayanda station and we recorded the readings in the range 60 to 90. But as soon as we traveled to Mira Road in a polluted environment where there were many vehicles nearby and also a pawn shop, the readings were in the range above 120, and some readings also exceeded about 160, which is not normal for asthma patients. Like they can get a severe asthma attack if they are exposed too much to such high concentrations of AQI. This second graph represents the journey of Cooper to RA, wherein you can see two dips in between. These two dips occurred when we traveled from Andheri to RA in a metro. So, for a metro, an AQI reading of 40 is quite normal and safe for asthma patients. But as soon as we reached RA, we recorded an reading of approximately 110, which is not normal for a green area. This graph is of Vasai East and West, where there is a construction site, and as you can see, there are spikes of above 180 and 200, which is normal for a construction area but not normal for the asthma patients. See this data we have just received now, as we are in a very polluted area. And finally, the cost. The sensors are the main expense, around 5,700. This is important for considering affordability and scalability. Thank you. This is how our AI system can make a real difference for asthma patients.